Hello everyone, today I'm going to talk to you about simple trusses, the method of sections. This is the textbook I used for my course. So basically, when is it appropriate to use the method of sections instead of the method of joins? When we want to know the forces in every member, we can use the method of joins. Like in this problem over here where we wanted to find the forces in each of the members, CE, DC, DB, BC, and AC. When we want to know the forces in just a few members, we can use the method of sections. Like in this example over here, where we only wanted to know the forces in the member BD. The number of unknowns we can solve for in the method of joins versus the method of section is also different. In the method of joins, we can only solve for two unknowns because in joins, you only have a point object and all the forces are concurrent on that point. Like in this example over here, where we had the point E, and there are three concurrent forces acting on that point E. In the method of sections, we can solve for three unknowns because we deal with rigid bodies in the method of sections. We thus have an additional equation for the sum of the moments. Like in this example over here, where we had these three unknowns, FBD, FBE, and FCE. And basically, we calculated the moment about this point E. In the method of joins, it's also possible to sum moments. We would use the sum of moments to solve for some unknowns. But in the method of sections, we can we can always solve for three unknowns because we have an equation for the sum of the moments because we are dealing with a rigid body and not just a point object. So as you see, so let's work through an example problem together. So our given information, we start with a truss that looks like this, a truss of members and joints. We have three forces acting on the joints. Because this is a simple truss construction, we have force 1, force 2, and force 3. We have a roller acting on E, and then a pen acting on G. We want to find the force in the member BD, this member over here. The solution, first we will replace each of these, the roller and the pen, with forces. We have force EY, the reaction force at E, acting on E, and we only have a Y component of the reaction force there. At the point G, we have two reaction forces. We have an X component and a Y component. Generally, it is hard to know this, so sometimes we will arbitrarily denote an X component and Y component to both, but in this case, we already know that there is only a Y component of the reaction force at E. So we can only section a truss by cutting through a member once. We also have to go through the member we want to solve for, and we have to completely bisect the truss. So this is using the method of sections where we cut out a portion of the truss and analyze that part. So for instance, we can take a cut over here. Notice that we can only go through each member one time. So we have fulfilled that over here because we went through this member one time. This is our member of interest that we want to solve for. So we want to make sure we go through the member we want to solve for. So we already did that. We also went through this member one time and this member one time, and this this completely bisects the truss. Because all three components are bisected. This is one possible cut, but there are other possible cuts. Like this one over here, this is another possible cut. We note that we went through our member of interest that we want to solve for, another member over here, another member over here. And then we completely bisected the truss because we went through all components that it is necessary to go through and going through that direction. what is not a possible cut will be this one. A cut we cannot do because look, we missed out on bisecting this member over here. Like we just went over here. So this does not completely bisect the truss. So this will not be a possible cut. So returning our diagram, analyze either the left-hand section or the right-hand section because note that there are two sides to this. We have a left-hand portion and a right-hand portion. So which side will we choose to analyze? Well, of course, the side that has the lesser unknowns. We choose to analyze the left side because there are less unknowns to solve for, because there are no reaction forces to solve for. So basically, oh, sorry, this should be unknown. Because look, over here we have two reaction forces and another one. But on the left side, focusing on the left side over here, we only have two forces. We don't have any reaction forces at all. So let's focus on the left side. Replace our cut members with forces and assume those forces to be in tension. If we get a negative result, that will imply that it was actually in compression. But we should always assume that the forces are in tension because tension is assumed to be positive by default. So our cut members, we have three cut members over here. So we want to replace those members with forces because when we take away a member, there was a force acting on that member. So we have to make sure to include it to account for our simplification. This is the force, the free body diagram. We continue the line at E. To E, we have a force FBE, another force FCE, and another force FBD. And these are forces by each of the members that we cut off. Note that here we can determine three unknowns using the method of sections because the three forces are not concurrent, and we thus have an equation for the sum of the moments. So the sum of the moments about the point E, this point over here, will be equal to negative FBD times BC. Why BC? Because basically this distance over here, BC is equal to BD. We have simply moved the vector BD along its line of action. We have displaced this vector over here. And then we have noted that the R length, we have shifted this R length over here. So that's why. And then the next one is plus P1 times AD. And this will be a positive moment because the tendency is to produce a counterclockwise rotation. Plus P2 times BD. Again, we have moved BD, the R length down over here, and we have moved the P2 along its line of action and put it on this arrow over here. And then plus FCE times 0. So why 0? Because the distance over there from the point E is actually 0. We have moved FCE along its line of action and imposed it on this arrow over here so that its distance from the point E is actually 0. So we have no moment from the force CE. So FBD, the force BD is thus equal to 1 over BC times P2BD plus P1AD, as we see over here. Because the sum of the moments is actually equal to 0. Equals 0. The sum of the moments is equal to 0 because this whole structure is in static equilibrium. And that is our final answer. Thank you guys so much for watching this video. I hope this helped you with the analysis of trusses by sections, and see you soon for our next video.